speaker is Farzaneh Derakhshan, who will speak on session types, recursive processes, and infinitary.
Thank you. I'm Farzaneh, and I'm an assistant professor at Daily Institute of Technology. I want to start by thanking Abhishek and Anupam for organizing this session and for giving me the opportunity to give a talk here. My talk is about session type, the correspondence between session type recursive processes and their an infinitary linear logic. It's a work that I mostly did during my PhD, joined with my advisor, Frank Pfennig. But in general, my research is about designing good concurrent programming languages, and good can mean many different things, right? Safety, security, reactivity, fault tolerance. This talk in particular is about reactivity for message passing concurrent programs. And if you're interested to look into more details, you can look at our LMCS paper or my PhD dissertation. So let me start with a very simple example of a client-server communication and message passing communication. And it's an authentication scenario. So we have Alice, who is a client, and we have the server. And they are connected with a private message passing channel. So the idea is that Alice wants to authenticate herself, so she sends a token to the server, and now it's up to the server to accept or reject that token, and the server sends back a message to notify Alice about its decision. And then they drop this communication channel. Let's say both of them terminate. So as you can see, there are very good properties about this simple example. We have communication agreement. They both agree on who is going to send, who is going to receive. They're deadlock free, and it's terminating. And now the question is, how can we make all of our programs to have these good properties? So one solution is to use protocols or session types, which specify the order of sends and receives along a channel. So for example, in this scenario, the protocol would be send a token, receive a decision, and then be done. And something that I want to emphasize on is that protocols are dynamic. So with each communication step, the protocol evolves to a new step. So let's say that at the beginning, this is the protocol that we have. As soon as Alice sends the token, the protocol evolves to this one that says now Alice wants a decision. Okay, so there is a correspondence between this session type processes and linear logic established by Farzaneh Pfennig for the intuitionistic setting and Wadler for the classical setting. And this correspondence provides a very strong foundation for session types because it basically gives you all of these key properties for free with a very elegant proof. But the problem is that the correspondence is only good if you are in the terminating setting. As soon as you add non-termination, you want to write some interesting programs with recursion, this correspondence is gone. And the main contribution of this talk is to revive this correspondence, this time between recursive session types and a sequence calculus for an infinitary linear logic. So we are in the intuitionistic setting. So we are basically following Farzaneh Pfennig. So first I will give a very brief introduction into Farzaneh Pfennig setting. And I'll do that by, again, let's look at this Alice server example. This time we want to look at it with a linear logic in mind. So we have a configuration. Alice is connected with a channel to an external environment, and Alice and server are connected with a private communication channel. So each communication channel in this setting has a client, which is the parent, and it has a provider, which is the child. And to each channel, we also assign a name and a protocol. Now the idea is that we want to rewrite this protocol using linear propositions. Okay, so I want to make it simpler. So let's say that there are exactly two tokens in the world. It's either blue token or green token. So I can rewrite off like this, that Alice sends either the green or the blue token, and then server responds with either success or fail. Okay, so if I want to write it with linear proposition, this would be our protocol. It starts with additive conjunction, which basically means that it is the responsibility of the client to send a message to the provider. It will be from parent to the child. And the messages that it can send are only these two labels, green or blue. So basically the client can choose between the labels green and blue and send one of them to the provider. And what comes after this label is what the protocol will evolve to after this communication is done. And in this case, we start with an additive disjunction, which means that this time it's the other way around. Provider has to send a message to the client. And you can see that now, again, we have two labels, success and fail, which means that provider can choose between success and fail. Okay, so now let's write one particular implementation of this protocol in which Alice chooses to send the blue token and server responds to the green token with success, responds to the blue token with fail. And let's see how this will go. So you can see that server has two branches and Alice sends the blue label. Okay, so Alice sends the blue label. After that, the protocol evolves to this additive disjunction. And this Alice sending the blue label forces the server to choose the second branch. So server has to respond with fail. And the protocol evolves to 1, and 1 corresponds to just drop the communication, close the channel. And for sake of completeness, I will also give a protocol to the channel that connects Alice to the environment. Let's say that it also has type 1, which means that when Alice is done with communication with the server, it also closes a channel that connects it to the environment. Okay, good. So you can see that this particular implementation behaves as specified by the protocol. Now we need a type system to check any given implementation. And for the type system, we first need a typing judgment. The typing judgment is like this. We write the name of the process or the code of the process in the middle. What is on the left? On the left is the name of the channel that the process is a client of. And on the right is the name of the channel that the process is a provider for. So you can see that all is on the right side of server and it's on the left side of Alice. So this is our process judgment, and we have a set of rules based on linear logic with which we can type check our processes. For example, the derivation for Alice would be like this. And with these derivations, we read them from bottom to top. Bottom is the previous step, and so conclusion is the previous step, and premise of the rule is the post step. If we start from the bottom, you can see that we have in the previous step, we have Alice sending the blue label, which means that it forces the protocol of X to become this second conjunct in the previous step, and that is exactly what the second and left does in linear logic, right? And then after that, we have a case between success or failure, meaning that Alice has to be ready to receive both success and fail, which again corresponds to the fact that in plus left rule, you have both of these premises in the previous step. So statically, Alice doesn't know which comes next, so it has to be ready for both. And this means that we have two premises in plus left. And if I drop this process names and the channel names, I get this proof in linear logic or authentication proving 1. Okay, so far I showed you that how Farzaneh and Pfennig show that types are propositions and processes are proofs. Okay, so next I want to show how you can put two processes, the proof of two processes together to get the proof of the whole configuration. And we do it with a rule called cut, and they call it cut because, again, if you drop this process names and the channel name, you exactly get the cut rule in linear logic. And observe that the cut formula corresponds to the protocol name, the protocol that connects Alice and the server. Okay, now that I talked about cut, I have to talk about cut reduction. So here I have a cut with the full proof of server on the right and Alice on the left. We want to do cut reduction between this and left 2 that chooses the second conjunct and right that has to be ready or has to work with both of the conjuncts. And because and left 2 for in cut reduction, because and left 2 chooses the second conjunct, it also forces it forces us to choose the second premise of and right. And this is exactly what happens when Alice sends the blue label to the server. It forces the server to choose the second branch. Good, and you can see that the protocol that we evolved to after this step exactly corresponds to the cut formula after cut reduction. Okay, so we introduced the basics of Farzaneh correspondence. Types propositions, processes proofs, binary channel is cut rule, communication is cut reduction, and because we have cut elimination, it basically means that all of these communications can be done, and we have termination. But as I said, this solid ground is lost as soon as we add recursion. And next, I want to show why recursion, what is about recursion that makes this bad. So I want to, again, get back to this Alice server example, but now I want to make it more interesting. Let's say that we have 2 layers of servers. So Alice is connected to the tier 1 server, which is responsible for authentication and also for communicating with the client. But there is another layer of the server, which is responsible for storing and handling data. So the example starts as before. Alice authenticates herself by sending the token, and the server responds with a decision. But at this point, instead of dropping the communication, tier 1 server requests for data from tier 2 server. And let's say that tier 2 server gets back to tier 1 server by sending the data, which is an actual number. And now tier 1 server wants to do some work on this, some computational work on this natural number, and let's say that it computes the parity bit of the data and sends it back to Alice. So in this example in particular, I'm interested in the communication between tier 1 server and tier 2 server. Okay, so I call this channel Z, and let's say that I call the protocol L2 because it's the second layer. And remember our pattern. Okay, so now I want to write L2 using linear propositions. So this time L2 would be something like this. We have recursion, so we write them with the type variables and equations. I define L2 as, okay, so it starts with receiving a request. So tier 1 server has to send a request to tier 2 server. It is from the client to the provider, so we have an additive conjunct. And it's a unary conjunct because the only possible thing to send is the request. And then after the request, the protocol evolves to a natural number because now we want to receive a natural number from the tier 2 server, and the natural number is the standard thing is either 0 for successor, but in this particular case, when tier 2 server is done by sending the natural number, when it sends the 0 label, the protocol evolves to L2. So it is again ready to receive another request. Okay, so you can see that
these two are defined mutually. Okay, so to understand it a little bit better, let's look at one particular implementation of tier 2 server, which is a good implementation. It says that I receive a request, I send back number 1, and then repeat. And this will be the code that we write in session types. So it receives a request and sends number 1 with % successor, then 0, and then repeat. And in action, it would be something like this. Tier 2 server receives a request, protocol evolves to NAT. Now tier 2 server sends a successor. The protocol is still NAT. Now server sends 0. The protocol changes to L2, and it's again ready to receive another request. But before that, tier 1 server will now has the opportunity to compute the parity of the data that it received, because the data is complete. So it will get back to Alice by sending the parity bit of the data. So you can see that this program is not terminating. It doesn't terminate. You can send requests forever. It can receive the request forever. But the point is, it is reactive, because at each loop, it actually produces the data, and it gives the opportunity to tier 1 server to get back to the external environment being Alice. Okay, good. Now I want to show a bad implementation of this tier 2 server. So tier 2 server receives a request. The protocol is NAT. Tier 2 server gets back to tier 1 server with successor. Protocol is still NAT. Tier 2 server again gets back to tier 1 server with successor. Protocol is still NAT, and actually it will always send successor. Yeah. So you can see that this program never terminates, but it also never produces an actual data, and it never gives the opportunity for tier 1 server to get back to the external environment with the parity bit. Here is the code for this program. You see that S2 receives a request, and then it will get into a loop that just sends successor forever. So this is an example of a program that is not reactive. But one interesting thing is that both of these programs have progress on preservation. They adhere to the protocol. They have communication agreements, and there is no deadlock. They will. There's at least one process that can take a step at each one. So what we want is not is something more than these two. What we want for reactivity is a stronger form of progress that says each process either terminates or communicates along one of the external channels after a finite number of steps. Okay, so now I will show how we can build this correspondence with infinitary linear logic to ensure this is a stronger form of progress. Okay, so I have to mention that in this work, we don't work with the full linear logic. We work with the additive fragment of linear logic, which instead of, as you guessed, in all of my examples, I only had a chain. So instead of having a rooted tree, I only have a chain of processes. But the interesting thing is that even if you are working with this small fragment, which is called sub-singleton fragment, it is very powerful. It has it's Turing complete, basically. It has a power of Turing machines. Okay, so now let's take a look at this query-forward correspondence that we established. Okay, so the first step to establish this query-forward correspondence is to redefine our session types as least and greatest fixed points. So in this example, in our previous example, I rewrite my session types. L2 will be the greatest fixed point, and this NAT will be the least fixed point, as you could guess. So it is okay for L2 to it is okay for server 2 to receive infinitely many unfolding messages of L2, but in each cycle, it can only send finitely many unfolding messages of NAT. So NAT is the inductive type, the terminating type. L2 is the productive type for the greatest fixed one. Okay, so this notation is different from what we saw in the previous talk that you used, like mu as a subformula. Here we use with type variables and equations, but they're basically equivalent. But as you can see, like L2 is defined with NAT. NAT is defined, L2 is defined based on NAT. NAT is defined based on L2. So they're mutually defined. And to order them, we need this superscripts 1 and 2 that is basically like the subformula property if you, no, not properties, the subformula order if you write them in the format that we saw in the previous talk. And we'll see what this priorities. So it basically means that L2 has a higher priority than NAT. And we'll see how it will help us build our validity condition and prove a strong progress later. Okay, so one thing that comes after we add this change using least and greatest fixed point is that now processes cannot just implicitly unfold the definition, they have to explicitly send unfolding messages. Okay, so it means that, and okay, yeah, so who sends this unfolding messages? For greatest fixed point, you can see like greatest fixed point are very similar to conjunction. So they're we call them negative types. So the unfolding of greatest fixed point will be from the client to the provider, and the unfoldings of least fixed points are from provider to client. So let's see how we can rewrite our code. If this is the code for the bad implementation, you can see that before working with L2, our server tier 2 server has to receive an unfolding message to unfold the definition of L2, and then it can receive the request. Similarly, before sending a successor, it has to send an unfolding message and then send the successor label. So this code will correspond to this cyclic or circular derivation on the right. And again, remember that we have to read this rule, this derivations from bottom to top. So it means that we start with L2 on the on the pre-step. Then there is a mu right applied on L2 to just unfold the definition of L2, and this corresponds to tier 1 server sending L2 to tier 2 server and doing the unfolding. So now after unfolding, our protocol evolves additive conjunction. So now we can apply this and write, which means we will send a request to tier 2 server. Now the protocol evolves to NAT. We will now it's the obligation of tier 2 server to first unfold NAT. So we with mu write we send tier 2 server sends an unfolding message to tier 1 server. Again, the protocol evolves to the definition, and then there is a plus write 2, which says choose the second disjunct. So tier 2 server sends the second label, which is successor. And now we get to this cycle. And the cycle means that we identify this open subgoal with one judgment in the derivation. So it means that whatever that you apply, the proof will continue with whatever that is applied on the previous proof for NAT. Which means that again we apply this mu write rule, another unfolding message. Again we apply this the plus write 2, another successor, and this happens forever, exactly like the loop circular call. Okay, so with that, we established that recursive session types are basically least and greatest fixed points, and recursive processes are circular derivations, and recursive calls in particular are circular edges in the derivation. Okay, so similar to the previous correspondence, we also want to show that communication is cut reduction. In particular, internal communication is internal cut reduction. So for that, I'll put the the derivation for tier 2 server, the derivation for tier 1 server, and cut them together to get the derivation for the whole configuration. You can see that, like, on the left, for the whole configuration on the left, we don't, we are not the client of anything, but we are the provider of type bits, which connects us with Alice. Okay, so yeah, so we want to, let's say that we want to eliminate this cut. If you are in the Infinitary setting, you start from the top, you eliminate cut, you get to the next cut, you eliminate that, and so on and so forth. And because it is finite, you can eliminate all the cuts in Notion. But here there is no top, so we have to start from the bottom. The idea is that you look at this cut, you see like you look at the last step of both of these derivations. If there is if both of them are principal formulas, then you apply internal cut reduction. If one of these, if one of them, the cut formula is not the principal formula, this is perfect because it means that another rule has applied, which is not on the principal formula, so you can just output that rule. So basically, in the best case scenario, you can there are finitely many cut reductions that you can apply, and then you get to one non-principal last step that you can output it, which means that your cut elimination will be a productive algorithm. So the cut elimination again may not terminate, but in this case it will be productive. But the worst case scenario is that these cut reductions never actually terminate. So you have infinitely many cut reductions. And this is exactly what happens here. We start, so you can see that L2 is, the cut formula is principal in both. So we have to apply cut reduction. After that, the cut formula will become this conjunction. Again, we have to apply cut reduction. It will become NAT. Again, it's principal in both. We have to apply cut reduction. The definition of NAT, again, principal in both, we have to apply cut reduction. And because in plus right 2, we choose the second disjunct, the cut reduction will choose as the second branch. And there is a circular derivation, which means that again, this becomes internal, and you have to apply this cut reduction forever. So cut elimination in this case never terminates. Exactly the reason why our tier 2 server makes the configuration non-reactive. But if at any point we choose the first, the tier 2 server allows tier 1 server to choose the first branch, then then we apply some rule on the bits, then there is an external rule that we can output, and our algorithm becomes productive. Okay, so getting to this end, we established these three. Now we established that internal communications are internal cut reduction, and we established that cut reduction may never halt. So the solution that they use, like in the Infinitary linear logic community, is to introduce a validity condition that enforces termination of this internal cut reduction. And there are many validity conditions. All of them have the same flavor, but in particular, I want to talk about the validity condition introduced by Fortier and Santognale, because they, like us, work on the sub-singleton fragment. Okay, so the validity condition basically says that each cycle has to be supported by the unfolding of a least fixed point on the left or a greatest fixed point on the right, with one side condition that the supporting fixed point for each cycle has to have the highest priority. In the next slide, I'll try to explain why this is the case, or why it makes sense. Okay, so here I put the bad implementation, the derivation corresponding to the bad derivation of tier 2 server. We have one cycle, and the only fixed point that occurs in that cycle is mu right, which is not good enough for our validity condition. So this is considered invalid, and we want it. So now on the right, I put the derivation for the good implementation of tier 2 server. You can see that in the cycle, there are basically three applications of fixed points, new right, then two mu rights, right? So now we have to, so new right is good, but we have to make sure that it has higher priority. So L2 has a higher priority than that. And it is in fact the case. So we consider this program as valid. And this, again, corresponds to the idea that if this program is productive, but it allows a finite number of unfoldings of NAT between each cycle. Okay, good. So with this, I introduced the validity condition. Now, it is only natural that we also need a corresponding condition to validity conditions in session types, and we call this condition guard condition. Okay, so we choose to define our guard condition to be more restrictive than the validity condition for circular proofs. The reason is that we want it to be syntax directed and, more importantly, local in the sense that each process can be checked separately. We need it because, you know, we want, first of all, we want asymptomatic complexity to be linear. We want it, so we have an implementation of this guard condition. We want to how to precise error messages, and we want our definition to be modular. So if I change the definition of one program, I don't want to check validity of every other program that it depends on. Okay, and we proved that our guard condition is basically a stricter version of validity condition for TNS. And with that, we can prove that the strong progress actually corresponds to path elimination, which allows us to prove our main theorem that if a program is guarded, it has a strong progress property. It always terminates either in an empty configuration or one attempting to communicate along external channel. So I want to conclude, but before that, I want to bring up two important points. First of all, I told you that this subsingleton fragment is Turing complete. So we proved that this termination of Turing machines actually can be reduced to strong progress for session type processes. And because of the halting problem, it means that no matter how you define your validity condition, guard condition, there will be some good reactive processes that are, we call them invalid. And because of that, so we are thinking, we thought about, okay, so if this syntactic thing doesn't work, then we need a semantic predicate to describe the validity condition. And we define this semantic predicate indexed by the type of the configuration. And we define it in a meta logic that itself is a first order linear logic. It's a first order predicates with least and greatest fixed point. So I show you like the predicates that we define. We have two predicates. Configuration of P encodes the semantics of process P, and the second predicate Y being of type P encodes the fact that the property that Y either terminates or receive a message after finite steps, and we define them like following Miller's processes as formula. And then we prove something similar to fundamental inadequacy theorem, say that if a process is locally guarded, then there is a proof for this predicate, and if there is a proof for this predicate, then we have strong progress. Great, that's it. And of course, there are several prior books that I didn't have time to bring across all of them, starting from infinitely branching groups to finitary groups with fixed point or infinitary groups with fixed point, and also Miller's processes as formula. Yeah, this concludes my talk, and thank you. Well, okay, so no, you didn't miss it. I didn't put it in the slides. So the idea of the art, you mean, why is it local? We have a type checker for a guard condition. It's basically a lexicographic induction between like some measures that we assign to each channel. So we define a lexicographic induction, and at each step we show that it either goes down or it remains the same. And the guard condition would be at the end of the cycle, you have to check that the lexicographic induction.
Useful and what kind of challenge?
Yeah, that's a great question. So it's definitely useful. I mean, like, I put it in the future work. So both multiplicated fragment, because now it allows you to, send processes, like you can have higher order processes. The problem that we had with this multiplicative version is that so when you have a lolly, it behaves like a function, right? So you want some relation between the input and output, basically. So the validity conditions for infinitary proofs that exist in the literature do not capture this. So if we use the validity conditions that exist in the literature, we won't be able to capture the relation between the input and output, which makes our our guard condition very restrictive. Yeah.
I guess my previous practice that your system gives you this guarantee that you have reactive, and you feel that it's impossible to get perfect to in the spirit of this bug finding, correctness reasoning that we is it possible to find a kind of invalidity condition where you'd be able to prove that something was long-term?
I see. So do you mean some kind of under approximation instead of over approximation? Yeah, I have to confess that we never thought about it, but it's an excellent idea. Yeah.
He calls it on the proof system. It would give you better complexity.
Yeah. And so I think it definitely makes sense, but what do you want to achieve other than complexity? Because we want to achieve, modularity. If you have modularity in mind, sure, we can do that. So if you have two circular proofs that both of them refer to each other, if you check one, you don't want to check the other one. But it is restrictive, and it's not like the restrictiveness is quite long. So it makes sense if you want modularity.